The last primitive type we need to talk about is char, the type that allows a variable to hold a single character. Even though it feels to us like the computer stores names, music, video, and games, it really only stores numbers. So in order to store characters, we need a mapping that associates each character with a number.
This is a lot like the suits in the card and deck lab. We needed to represent 4 distinct suits, but we stored them as numbers. Zeros meant spades, 1 meant hearts, and so on. Then we built our toString to translate and display what the number meant instead of just displaying the number. We need to do the same thing for characters. Decide which number is associated with each character, and then, when the computer outputs the character, it uses that number to decide which character shape to draw on the screen.
Early on, IBM created a character-to-number mapping that was called EBCDIC, Extended Binary Coded Decimal Interchange Code. The way to read this is to build the integer by concatenating the row and column of the character you want to encode to find the number associated with that character. For example, lowercase f is 134. Two things people notice about this. First, it isn't using all of the possible values. That's true. There are some control characters, things like carriage returned, that aren't shown here. But even with those, it doesn't use all the numbers. Second, that looks like chaos. In this way of looking at it, I agree. However, this is the same mapping, but instead of using base 10, it uses base 16, hexadecimal. If you aren't familiar with hexadecimal, don't worry. Just understand that it isn't quite as chaotic as it seems. At the same time as EBCDIC, there was a competing standard called ASCII. Yes, you pronounce ASCII as ASCII, and it stands for the American Standard Code for Information Interchange. The first difference we notice is that ASCII uses all of the values. Some of them look weird because they aren't really printable characters.
When Merlin was learning to program, computers didn't have speakers. They only had a single beep the computer could play. This was the only sound a computer could make. That beep is one of the unprintable characters in ASCII. They use the value 7 to ring the beeper.
Yes, Zumi, I'm old. I get it. But sometime you should Google the amazing things people did with that one beep. Anyway, the more important thing to notice is that in ASCII, the capital letters, the lowercase letters, and the characters representing digits are in consecutive groups. That wasn't true for EBCDIC. Since those things are in groups, we can do some magic. In our code, when we want to use a character, we surround it with single quotes. Consider the condition in this if statement. It reads as, if CH is greater than or equal to capital A, and CH is less than or equal to capital Z. More simply, it means if CH is between capital A and capital Z inclusive. Looking at the chart, only capital letters are between capital A and capital Z, so this condition will be true only if CH contains a capital letter. Because both the uppercase and lowercase letters are in consecutive groups, we can do some simple math to convert one to the other. The distance between the lowercase version of any letter and its uppercase counterpart is always the same, so we can use that distance to convert them. For example, the distance between capital A and lowercase a is 97 minus 65, which is 32. Adding 32 to capital A will give you lowercase a, and subtracting 32 from lowercase a will give you uppercase a. The same is true for every other letter. Uppercase M is 77. 77 plus 32 is 109, which is lowercase m. To code that conversion, we just have to remember that lowercase letters have values larger than uppercase letters. With that, instead of memorizing the distance between the upper and lowercase letters, we can calculate it with lowercase a minus uppercase a. Subtracting that distance will take a lowercase letter and convert it to its uppercase equivalent. Alternatively, adding that distance to an uppercase letter will give you the lowercase equivalent. It's important to remember that the character for 0 is different from the number 0. The character 0 is how we write it down, where the number 0 is a quantity. we encode the character 0 as 48.
Yeah, that seems kind of weird. Notice that the number 0 doesn't map to a character at all. We often try not to use 0 because memory that hasn't been set up often contains zeros. This means it's easy for bugs to make values be 0. We wouldn't want bugs to give us real characters.
And, like the letters, the digits are sequential, which lets us make a similar check for is a character a digit. It's a digit if it's between the character for 0 and the character for 9 inclusive. Given that the character of a digit and its numerical value are two different things, we'd like to be able to convert between them. We can convert a digit to the number it represents by subtracting the character 0 from it. To see why that's true, play with a couple of digits to see why it works. And with what we've already learned, I bet you can figure out how to convert a number that is between 0 and 9 to its respective character.
You could back up the video to see the ASCII table to think about it.
The bottom line is that these tricks don't work in EBCDIC because the groups of letters aren't consecutive in EBCDIC, and ASCII encoded more characters. As a result, ASCII is much more prevalent than EBCDIC. While ASCII was good for us, it's really English-centric. Early developers didn't think about trying to encode characters that are used in the other languages. Clearly, we needed something better. The challenge was that we had already used up all of the values in ASCII. ASCII characters fit into 8 bits, and therefore only 256 characters can be mapped. So the people who make these standards doubled the size of the memory the character mapping uses.
Doubling the amount of space does way more than double the number of values it can hold. Imagine that the mapping used 3-digit numbers. That would have 1,000 values. Double it to 6 digits, and you have 1,000,000 values.
So when they doubled the encoding, they went from 256 characters to now space for 65,536 characters. The result is Unicode, and it has mappings for characters from many languages, and even space for mapping of things like emoticons. So, when we store characters, we store them as numbers, so we need to have a mapping between characters and integers. EBCDIC and ASCII were early attempts at this, but each has its weaknesses. They were replaced by Unicode, which has space to support a wide variety of languages and control characters. And when they designed Unicode, they incorporated the mappings that had already been agreed to in ASCII for backwards compatibility.